Hello everyone, so my name is Chen-Yu, and I'm happy to be here to share our work, which is the Seraph toward the scalable and efficient fully external grade computation via the on-demand processing. And this is today's outline, so I will go through the introduction, the background and the motivation of this work, and then we'll present the Seraph, which is the proposed system, and finally we'll give the evaluations. So to begin with that, we'll talk about the importance of the graph and the graph system. So the graph are the well-known data structures, and they are powerful data structure to describe the relationship in the real world. So they store the entity as the vertices and the connection between entities as the edges. And they have been widely used in the different fields such as the networking, the social media, and the bioinformatics. And due to their popularity, there are many kinds of users that would like to extract the various information from the graph efficiency. So again, this background that the graph systems are proposed to optimize the execution of the graph algorithms. And based on how we're going to use the memory and the storage, that the graph system can be actually divided into the three different types. That is the shared memory, the semi-external, and the fully external, respectively. And this slide shows the architecture of these three types of the graph systems. So the first one, the leftmost one, is the shared memory one. So the shared memory actually keeps the entire graph data in the memory. And for the graph data here, what I meant is the vertex data plus the edge data. And I use the big O of V to represent the size of the vertex data, and the big O of E to represent the size of the edge data. So in the shared memory graph system, that we will keep the entire graph, which is the big O of V plus the big O of E inside the memory. But this kind of graph system will actually have a lot of memory consumption. So semi-external graph system, that is the middle one, is proposed as a trade-off. It can alleviate the memory consumption. It stores the larger size the edge data in the storage and keep the smaller size of the vertex data in the memory. And the final one is the fully external one. So the fully external actually store both of the vertex and the edge data in the storage. So this architecture that only requires a very small amount of memory for the graph processing. And the fact is, this small amount of memory is actually independent from the graph size. So in here, I use the big O of C to indicate that it's actually just a constant amount of memory. And no matter how the graph grows in the future, that we can use the big O of C to process the graph. And each type of a graph system can actually has its trade-off between the memory consumption and the execution time. And to investigate their trade-off that we present this figure, that the x-axis in this figure actually shows the memory consumption, and the y-axis here is the execution time. So the first system we present here is the shared memory one. So as you can see here that it actually achieves the best performance, but it will require a massive amount of memory to run because the entire graph needs to be kept inside the memory. So the second system we present here is a semi-external one. So this type of graph system is a trade-off. So compared to the shared memory one, that the shared memory graph system can use much less memory, but correspondingly, that its execution time is around 2 times slower than the shared memory one. And for the final one, we call it the fully external. So this type of graph system demonstrates the appealing feature that is that it can process any size of larger scale graph with only a constant amount of memory. So in this experiment, the big O of C here is around 5 or 6 times smaller than the big O of V. But however, we can also observe a pretty fatal issue in this fully external graph system, that its execution time is around 5 times slower than the semi-external one. So based on this investigation, that the goal of this work is to present the Seraph. So the Seraph is a fully external graph system. So in other words, that it retains the appealing feature that the processing the large-scale graph with it can process the large-scale graph with only a constant amount of memory. But furthermore, is that compared with the other fully external graph system, that its execution time can be greatly improved. So we position Seraph as an efficient fully external graph computation system in this spectrum. So the next part we will discuss about the background and the motivation of this work. And when it comes to the fully external graph system, that the most fundamental issue here is how we're going to restrict the memory usage. And this can be achieved with the technique we call it as the grid-based format. So the grid-based format, there are several steps to do in a grid-based to store a row graph into the grid-based format. So the first step is that it will try to divide the vertex into a multiple disjoint vertex partitions, and each partition contain a similar number of the vertices. And based on the partitioning result, that we further divide the edges into the disjoint grid. And it's worth noting that every edge in the grid, they will share the same locality in terms of the vertex partitions. So for example, like every source vertex in the grid, they will belong to one vertex partition, and every destination vertex in the grid will belong to another partitions. And with the help of the grid format, that we can form a subgraph by just using 2 vertex partition plus 1 corresponding edge grid. And this concept can effectively restrict the memory usage because we don't need the entire graph for the grid processing. We just need to process one subgraph at a time. So on top of the grid format, that the existing fully external graph system that generally apply the streaming-based processing. So this means that they compute a graph by streaming the edge data in a grid-based granularity. So using the streaming-based processing can enjoy the high sequential access speed, but the bad issue is that it often loads the excessive and irrelevant data because it will activate a grid in a grid-based granularity. So it will read the entire grid even if we only need a several bytes from it. But this design principle can actually make sense for the traditional storage, such as the hard disk drive, because the hard disk drive has HDD has a wide gap between the sequential and the random I/O access speed. But for the modern storage, such as SSD, this kind of storage can actually deliver a comparable speed between the sequential and random access. So the streaming-based processing does not make sense to use on those type of modern storage. So based on this observation, we try to seek a different principle that's called the on-demand processing. So on-demand processing scheme can save I/O by reading only the necessary data, and meanwhile we can also leverage the decent speed in a random access. And this slide we show is the motivation, where we study the grid graph, clip, and the grid graph ODP in this slide. So the grid graph can be viewed as a baseline system which adopts the streaming-based processing. And the clip is an improved version of the grid graph. So the clip actually accelerates the convergence of grid algorithm over the grid graph. So the clip in here can be viewed as an advanced version of the streaming-based processing. And to fairly compare the streaming grid processing and on-demand processing, because they're existing where they are based on our survey, there's no existing where they fully support the on-demand processing in the fully external graph systems. So to fairly compare the streaming-based processing and on-demand processing, we implement our own system that's called the grid graph ODP. So the grid graph ODP, it also follows the grid-based format, so that it can support the fully external grid computation. But furthermore, we convert the streaming-based processing into the on-demand processing. So the grid graph ODP here, it can be viewed as the baseline system which adopts the on-demand processing. And in this motivation, that we evaluate with 4 types of storage drive, which are the HDD, the SATA SD, NVMe SD, and the ULSD, the ultra-low latency SSD. And for the result, we can first observe that clip is basically always better than the grid graph on the old type of the storage drive. So this result is not surprising because clip and the grid graph are pretty similar to some degree, but the clip is actually an advanced version of the grid graph because it can just improve the convergence of the grid algorithms. So clip basically is better than the grid graph on all type of storage drive. But when it comes to the grid graph ODP, it has become a different story because we can see that when we test on the HDD, the grid graph can actually perform the worst among all systems. So this is because the grid graph ODP cannot they fail to exploit the sequential access speed. But for the modern storage, including such as the other type of the storage drive, including from the SATA SD to the ULSD, the grid graph ODP can actually perform better because the on-demand processing is actually a better method to save I/O while to leveraging the decent speed of the random I/O access. So these results are actually interesting because we can see that the baseline system with the on-demand processing can actually show a better performance than the advanced system with the streaming-based processing. So these results are actually give us a direction to build a fully external graph system that on top of the principle of on-demand processing. So for the next part, we will present our system that is Seraph. So we developed Seraph based on the principle of on-demand processing because of the motivation. And moreover, we propose 3 practical design that is designed based on the framework of the on-demand processing to achieve the further performance improvement. And they are the hybrid format, the vertex passing, and the selective pre-computation. And the following, we will explain this technique one by one. So for the first technique, we will try to explain the hybrid format. But before we introducing a hybrid format, we need to first talk about the motivation of it. That is, why we cannot just simply use the traditional format to store the graph data. Why we need to invent a new format. And the reason is that there will be a trade-off to consider if we apply the on-demand processing on the traditional format. So in this figure, that we can show that the left one shows the grid format and the right one shows the row format. So the grid format is discussed before, so I'm not talking about it here. And the row format can be imagined as the same as the grid format, but with that the number of partition is equal to 1. So compare with the row format, that the grid format will cause 2 issues. The first one is it will cause a fragmented edge list. So this means that an edge list of a vertex is split into a different grid, so that we need to issue more IOs to retrieve the edge list of a vertex. And the other issue is that you will have the multiple index data, because we need to locate all the edges in every grid. So the overhead of reading the index data is actually proportionally increasing along with the number of the partitions. And on the other hand, that the grid format, the drawback of the grid format is that it does not provide a good locality of the vertex access compared to the grid format. Because we can see that when we compute the grid format, that we only need the vertex attribute from only 1 partitions. But on the contrary, that when we do the computation on the row format, that we would need to randomly access the vertex attribute. And this means that we need to access all the vertex partitions when we do the computation on the row format. So based on this observation, we try to propose the hybrid format. So the hybrid format is actually try to combine the row and the grid format to exploit both of their advantage. So in the hybrid format, if the edge block is dense, then if the edge block is dense, then we can actually expect that there will a lot of vertex attribute accessing during the graph computation. So, which means that we need a good locality in this case. So we will store this block into the grid format to have to enjoy its good locality for the access. On the other hand, if the edge block are sparse, then we will keep them in the row format because this can alleviate the issue of the fragmented edge list and the multiple index data that we have discussed in the previous slide. But however, the solution here is still not good enough because as we can show in the feature, the execution on the vertex 3 will still require the data from all the partitions. So the execution on the row format will still lead to the bad locality access. So to further address this issue, we propose another technique called a vertex mapping to complement the drawback of the hybrid format. So to put it simple, the main idea of the vertex passing is to delay the vertex write as logs, and then we want to create a good locality of the vertex access. And in this example, we try to write the attribute of the vertex U and the vertex V. So, and in this example, we are currently compute the partition 0. So the vertex U should be inside the memory. So in this case, if the vertex U is already inside the memory, then we can just perform the degrade update. But on the other hand, if the attribute, for example, like the attribute of the vertex V is not in the memory, then in this case, that our vertex passing will be enabled. So the concept of vertex passing is pretty simple. It just try to delay the write to the attribute and then try to lock the write into the buffer. So and then this log will be stored in the storage eventually to minimize the memory overhead. So the next time when the partition I is inside the memory, then we just merge those in storage logs back to the vertex attribute. Okay. And the final one is, so the third technique that we present here is the selective computation. So the motivation of this technique is that although the undefined processing try to read the necessary data, try to only read the necessary data only, but the fact is a common I/O block is typically larger than the edge disk. So this mismatch can actually provide us the chance to process the current active vertex and the future active vertex simultaneously, so that we can have the chance to increase the utilization of the loaded data, and therefore we can reduce the total I/O. And there are two steps in this pre-computation. The first step is that we will try to determine the list of the active vertex, which means that we need to determine what kind of vertex we need to process. And from the perspective of our I/O reusing, we will only pre-compute the future active vertex that are stored closely with the current active vertex. And next, based on this decision, the second step is simply compute all the marked active vertex so that the pre-compute vertex can be skipped in the future iteration. So in this one, for example, like in this page P, the blue one is the current active vertex and the orange one is the future active vertex. So if we enable the selective computation, then we can increase the utilization of the loaded page P, and therefore we can have a better chance to reduce the I/O further. And the final one I will present the evaluation. So this way is our evaluation setup. So we compare our system Seraph with other state-of-the-art systems. They are including the fully external, semi-external, and the shared memory. And the 5 graphic algorithms are evaluated, and these graphic algorithms are well studied in the other papers. And for the graph data, we evaluated 4 graphs. And the largest graph is the array graph, and its graph size has the 1.7 terabytes. And this measurement is based on the row graph data size. So this slide we shows the evaluation with the fully external graph systems. So the first row shows the execution time, and the second row shows the I/O amount. And in general, we can actually observe that execution time shows a similar trend as the I/O amount. And in particular, that is, if we have a less I/O amount, then typically means that we can actually result into a faster execution time. So in here, we can see that, in summary, that the server can actually outperform the grid graph vPar and CLIP by a significant amount of the ratio. So this slide we further evaluate the memory scalability. For this one, we also include the graphening and the LightGraph Plus. So under the fully external, we can see that the server can actually show a graphical effectiveness than the other fully external graph system, because it can use less amount of memory, yet it can achieve a better performance. But when we consider the semi-external framework, that is, we run this graph of Seraph in the semi-external framework, that we can observe that the Seraph can improve the graphene by around 24.1% on average. When we compare with Lego Plus, the Seraph semi is around 1.83 times slower, but it can save around 7.2 times memory. And the conclusion is that, so this work developed the Seraph is an efficient, fully external graph computation system that enables scaling the graph processing for the large-scale graph on the single machines. And Seraph is developed based on the principle for on-demand processing. And there are 3 design proposed in Seraph for the further performance improvement, which are the hybrid format, vertex passing, and selective computation. And the evaluation shows that the Seraph is an efficient, fully external graph system. And yeah, this concludes my presentation today, and thank you for listening and attention.